I was worried I'd have to restart the video. Okay, let's hopefully I don't have any more glitches. And you can see me okay too, right?
Yeah.
All right, sorry about that. You have exam 4 on Friday. The exam will have 5 problems. They're a little bit they're shorter than I normally give. Like on the exam 2, the problems are a bit longer. These are a little bit shorter. So there's 5 problems. Actually, there's 6 problems. You've got to choose 5. There will be a section where you got to do all 3 problems, and another section where you got to do 2 out of the 3. Okay. Really go over your homework. All right. The homework that you've done on WebAssign, make sure you go over them. Focus on the techniques you used. And if you understand how you did your homework, I think you should be fine on the exam. In other words, you can do one of the problems, you can look at the problem and say, oh, I can start it. You know, if you can do that, then you'll be fine on the exam. Okay? And, you know, it'll have a few short answer questions too. So you can go to the old Sierra College Physics website, the link that I gave you a while back, and you can look at, on there it's exam 3, okay? If you look at exam 3 on the old Sierra College website for this course, you will see sample exam, and you can use that to practice on. You can also, if you want to challenge yourself, you can try the online exam practice. So you can try that one too. That one has a key. They both have answers to them, so you can try them both to get ready. Additionally, there's a set of conceptual questions for this unit, and you can go over them. Although really, those conceptual questions, you should go over them as we cover the material. Any questions regarding the exam? Okay, you should be working on the motor lab this week. You should be working on building your motor. And hopefully you can come in on Friday and test your motor. Don't wait till the last minute. I know, that's a lot of students do that, but if you get started now, you have plenty of time to test it and make any modifications you need to. And usually the modifications are minor. Okay. The chapter 31 homework is due Thursday night. And so remember, exam 4 is on chapters 29 through 31. I will start chapter 32 today, but that will not be in the exam. Only chapters 29 through 31 will be on the exam. Okay? All right, so my objectives today is really to talk about applications of Faraday's law and then talk about self-inductions. And I spelled inductor wrong. All right. So last time I introduced Faraday's law. And Faraday's law is the time derivative of the magnetic flux through an open surface that's enclosed by a loop. Okay? That loop need not be a real physical loop. And we were able to see that this really is composed of 2 different parts. If you actually use vector calculus, and I don't expect you to know this, you can actually break this up into 2 separate integrals. One involving the time derivative of the magnetic field, and one involving the change or the change in shape of a circuit, or involving a moving circuit. If you integrate the electric field around a loop, which also consists of two parts. The induced part plus the V cross B part. You will see that the induced part of the EMF is a result of the time-varying magnetic field. In other words, the integral of E induced dot ds is equal to minus the integral of the time derivative of the magnetic field with respect to time. And this is a partial derivative because we're only looking at the time variation. We're not looking at how the magnetic field varies with x, y, and z. It's just the time part of the derivative that we're looking here. Okay? And so the induced part, which produces the electric fields that circulate like the magnetic field, comes from the time-varying change in the magnetic field. Okay? Whereas the motional EMF, this is really as a result of the fact that there's an electric field created in a physical loop, a physical circuit that causes the electrons to move around the wire. And this V that we have here is really the velocity of the circuit, or the part of the circuit that's moving. Okay? Questions on that? So the first few examples that I did in lecture in the second half of the lecture last week, I focused on induced EMF as a result of a time-varying magnetic field, and then I looked at the case where we have a circuit that was changing its shape, or a circuit that was moving. Now the minus sign that you see up here has to do with Lenz's law. Lenz's law says that if a current is induced inside a circuit, a loop of wire, then the induced current opposes the change in magnetic flux. If we have a motional EMF, we have to have a physical circuit. Okay? So you actually have to integrate it around a real circuit, whereas for this one you don't. If you put a loop of wire in the presence of this magnetic electric field, then you're going to have a current in that wire because the electric field is going to make the charges move. And I did send you an updated version of the notes, and so what you're seeing in the on the screen are the updated version. So we did the example. Oops, not that one. With the rod in the magnetic field, the rod was moving to the right, and we calculate the induced EMF from this equation, basically. Now remember that in our example, V and B were perpendicular to each other, so the cross product is easy. Okay, there's no angle between. The angle between them is 90, so sine of 90 is 1. So I don't have to worry about the trig function. But in general, if the angle between these two is not 90, I'd have to figure out what the cross product is. Okay. And then we also did an example with a solenoid. That's a classic example. It's in your book, and you have a homework problem on it. Okay. So I just want to spend some time doing some applications of these ideas today. Oh, what happened there? Okay, this is about where we stopped last time. So suppose we have an airplane moving at a constant speed through a uniform magnetic field that is perpendicular to the plane's velocity. So let me draw a picture of that. I'm going to draw a big X as that for the magnetic field. Let's assume it's into the board. And I'm just going to draw the wings of the plane. Okay, that's not a good picture. Hold on a second. Let's pretend those are the wings of a plane. The plane is going that way. Okay, so what are some questions I can ask? Keyboard's not working. Is the flux changing across the wings? First question. Is B dot NDA changing as the airplane moves in the magnetic field? Well, the magnetic field is uniform. The wings are always in that field. This integral hold on, this marker just died. This integral, as the wings are in the magnetic field, that integral stays constant. Okay? Doesn't depend on time. Even if the plane were accelerating, the flux doesn't change. So if the flux doesn't change, what does that mean? Is there an induced EMF across the wings? Well, remember that there's electrons in here. The wings are conductors. Okay, there's electrons on this wing, and you have electrons in the magnetic field, the same as me pushing the bar to the right. On the magnetic field, and we know that on this bar the charge separates. So the charge will separate there, but once they get to the ends, they have nowhere to go. I don't have a complete circuit, and I don't have a changing flux. I don't have a changing flux in here. All the electrons are going to do is separate, I'm sorry, not the electrons, but the positive and negative charge are going to separate till they get to the edges of the wings. And that's it. You will have a potential difference across the wings. Airplanes actually develop a potential difference across the wings. But there's no current there because there's no changing flux. Okay? What if I replace that with a loop of wire, because the airplane wings are solid. What if I replace this with a loop of wire? In fact, I'm going to draw two different loops of wire. I'm going to draw this one. And I'm going to draw another one for comparison. As this loop of wire moves to the right, is the flux changing through the loop of wire? And the answer is no, because the magnetic field stays constant. What about this one? As that loop moves to the right, is there a flux change occurring?
Yeah.
There is one, right? So there will be a current induced. In fact, let's take a look at this one, and then we'll compare it to that one. Okay? So the flux is changing on that one, but it's not changing on this one. However, the positive and negative charge is separating here, so there will be an induced EMF here. But there will also be the same induced EMF here. So the potential difference between these 2 points is the same as the potential difference between these 2 points. You can't get charge to move then, right? These 2 wires do nothing. So there's the potential difference here equals a potential difference there. You're not going to get any charge to move. You need some sort of potential difference to get the electrons to move. Now what about here? Is there a potential difference here? Do the charges separate on this leg of the loop? Of course. It's in the magnetic field. What about this one?
No.
No. So now you have a potential difference between these 2 ends, right? And so that's going to allow, so now you have an electric field in the wire. And so that's going to allow the electrons, well, the electrons go this way. And so you're going to have a current going this way. The flux is changing because the area exposed to the magnetic field is changing. Same thing as this particular case. So in the example on the left, you do have a current in it. In the example on the right, you don't. Okay? Let's look at another conceptual question. A lot of the questions we do in this chapter are conceptual. There are some problems you could do. There are some problems we do mathematically, but they are, some of them can get very easily very mathematically challenging. So don't overcomplicate the problems on the exam involving EMF. All right, so suppose I have a current carrying wire. It's a green wire. That might be hard to see. Well, on the camera it looks almost invisible.
It's like barely visible.
Okay, I won't use green. I was trying to use green because we have so many green markers that are never used. Okay. I will get rid of that.
Now you know why you don't use them.
Yeah. I actually don't use them even when we're on ground. For a different reason. But anyway. I'll make it blue instead. I was trying to match the PowerPoint notes. And then I have a circuit. And this R just represents the total resistance of the, it's just a loop, not really a circuit, but it's just a loop. Okay, a conducting loop. Let's say the current is increasing. let's say di dt is greater than 0. What is the direction of the current that's induced here? There has to be an induced current. Why? Because, well, first of all, you have, if I use the right-hand rule, there's a magnetic field into the plane of the loop caused by the blue wire. And the flux is increasing into the board. Lenz's law says that the induced current in this loop opposes the change in flux. So the flux is increasing because the magnetic field is increasing into the board. And so the induced current has to produce a magnetic field out of the board so that it will oppose the change in flux. That means that the current that's induced has to be in the opposite direction. That'll produce a magnetic field out of the board that will oppose the increase in the flux into the board. Does that make sense? And we can calculate the current if we wanted to. In fact, later on I will show you how to calculate the induced EMF, and then once we know the resistance, then we can calculate the current. Now, if you wanted to calculate the electric field, that's a different matter. That's a more difficult problem. And that's because the magnetic field along the loop varies. So I can't use the method I used the other day to find the electric field. I don't know if you remember the problem I did with the solenoid. Okay? I can't use that method here because in this particular case, the electric field that's induced is not uniform because the magnetic field is not uniform. Okay? Questions on that? All right. Normally, when the class is in person, I do this demo. But I can't. I mean, I could do it here, but it doesn't work. You won't see it very well. Suppose I have a wire wrapped around an iron core. So that green thing is the iron core. And so when you wrap the wire around the iron core and you run a current through the wire, you produce a magnetic field. The iron becomes magnetized. So what happens when I flip the switch? I'm producing a magnetic field. But in the process of flipping the switch, I have a magnetic field that goes from 0 to some final value. That means I have a change in flux in that red ring, through the red ring that you see there. It's going to induce a current to produce a magnetic field in the opposite direction. And if the magnetic field is large enough, then the two magnets are going to oppose, they're going to repel each other. And if the repulsion is big, then the ring flies off. And so normally when I do this in class, I do this with a ring, and you see the ring hit the ceiling of the lecture hall. Okay. The current that's induced in that little red ring goes around the ring, and it's called an eddy current. If I were to take that ring and just cut a notch in it, I would increase the resistance. Let me go back. I actually cut a notch in that ring, that red ring that you see there. I would actually end up increasing the resistance of the ring, and the ring really, when I flip the switch, wouldn't jump off because the resistance is too high. My current that's induced will be small. Same thing with this example. If I drop a magnet through a ring, a current will be induced in the ring opposing the magnet. And actually the magnet would want to slow down. It'll actually retard the motion of the magnet. I'll do a demo, maybe December 3rd, the next time we meet, I will do this demo. But it'll be with a long copper tube and a magnet. And you'll see what I mean. If I cut a slot in that ring, the motion of that falling magnet that you see there is really not slowed down, because when I cut that slot, I increase the resistance and the current decreases dramatically, or it's almost zero. And so the induced magnetic field in that ring will barely oppose the field due to the magnet. So those are two examples of eddy currents. And eddy currents, in some cases, are not wanted, for example, because they dissipate energy. They're not wanted in motors. They're not wanted in transformers, because they dissipate energy due to heat. A transformer is basically two coils of wire, generally with iron around them, an iron core. The iron core gets magnetized when you run currents through the wires. To get rid of eddy currents in a transformer, what you do is you laminate the transformer. You actually take the core of the transformer. So you have basically an iron core, and you wrap wire around both sides. Like that. And what happens is when you have a changing flux here, let's say you put a time varying voltage, you have a changing flux here, it's going to induce a EMF in this loop. The iron core helps make as many of the field lines go through this coil as this coil. Okay? But the problem is there's also a current induced in this thing. If this has a resistance, it's going to take away some of the energy. And so what they do with these iron cores is they slice them into thin pieces and then glue them together. They're laminated. And that reduces the I squared R losses. So let me give you an example of eddy currents. I'm going to demonstrate this to you. I have here, and I'm going to get rid of the PowerPoint slide real quick here. And let me point this down. I have a magnet. Oh, by the way, this is aluminum, okay? This is aluminum. These are the poles of the magnet, so there's no attraction. All right? So There's no attraction between the magnet and the aluminum. Aluminum's not magnetic. So I'm going to have the piece of aluminum experience a changing magnetic field. What I'm going to do is take the aluminum and let it swing. All right, without the magnet, it swings like that. But now when they let it swing in the magnetic field, it almost acts like a pair of brakes. You have a braking system. It stops it. So do you see how I can use Faraday's law to build a system, a braking system, like on the car? Anybody have an electric car?
I have a hybrid.
Or you have a hybrid, you have a Prius?
Yeah.
And so what happens when you hit the brakes? Isn't the battery getting recharged?
Oh, yeah.
Yeah, because and what you're doing is you're having metal going through a magnetic field, like this guy. Now what happens if I cut slots in it? If I cut slots, I'm increasing the resistance. I'm making it harder for the electrons to move around. All right. Basically, you're trying to get the electrons to circulate. And so they move more easily. It takes longer to slow down. Okay? Whereas in this case, it stops like instantaneously. It's amazing how that works. Okay? Those are eddy currents. The eddy currents are formed inside here, inside the material. So it produces a magnetic field that opposes this guy, and so it slows down. Questions on that? May I let you think about the details of the direction of the field, etc. Now, take a look at this system. I have the yellow wire. Let's pretend it's a long wire. On the diameter of a conducting ring. The current moves to the left. Let's increase the current. Let's let the IDT be bigger than 0. What is the direction of the induced current in the green loop? What do you think?
Would it be 0 because it's... Well, so, or wouldn't it be into the board?
Well, your first answer was correct.
It'd be both because it's between them, right? It's kind of... There's like a balance. There's... On one side it's going into the board, on the other side it's coming out of the board.
So what's the flux then at all times?
0.
0. The total flux is always 0. So I set it up, the geometry is set up so that the flux is always 0. So I can increase the current however I want, but as long as you have that symmetry, the top half has, and the bottom half has magnetic fields in opposite direction, the total flux is 0. So there's no induced current. There's no changing flux in that particular case. Okay, let's do this example. I want to calculate the induced EMF for this system. And I'm really focusing on the magnitude of the induced EMF, okay? I'm not interested in, I'm not worried about the signs here. I don't know if you watched the video. There's some videos in chapter 31 that I put on Canvas. And so the instructor really doesn't focus on the plus and minus signs when he does the mathematical part. He just says, I'll calculate the magnitude of the EMF, and then, oops, let me fix my camera. And then I'll use Lenz's law to determine the direction of the current. That way you don't have to worry about the details of the math. You know, worry about minus signs, which is nice, it's convenient. Okay? So I'm going to follow that in this problem. So I'm going to calculate the magnitude of the induced EMF. So we have a wire carrying current to the right. And I have a loop below it. Just a loop. Let's say it has a resistance R. This distance is D. This is D plus A. And then the length is L. So I want to calculate, and I just want the magnitude of this thing. So I'm going to take the magnitude of this thing. I don't want to deal with the minus sign. Okay, so let me write it that way. So I don't have to write the minus sign now. Okay? I'm going to choose, since the magnetic field is into the board here, when I integrate, I'm going to choose N into the board. Again, I'm not worried about the minus sign here. Okay, if I were to try to figure out the direction of the electric, or set up the integral to find the electric field, which I really can't do here, then I'd have to worry about minus signs. But I'm not going to worry about that here. I am going to choose B and N in the same direction. But here's a problem. The magnetic field is not uniform. The magnetic field to a wire is mu naught, or at least a long wire, is mu naught I over 2 pi r, where r is the distance from the wire. Okay. And in fact, in our case, I'm going to define, this is the x direction, right? And then that is the y direction. So I'm going to put a y here because the field's in the y direction. I mean, the coordinate is a y coordinate. It's really not a coordinate, it's a distance. It's a distance in the y direction. So this thing varies with y. So what I have to do is realize that the magnetic field is the same all the way across, but it's not the same downward. So I actually have to break up my area into thin strips of length L and thickness dy. And so then dA is L dy. Okay, I have to break this up into thin strips so that B is constant over that strip. That's what I did there. So now, with B and N in the same direction, delta V, since I had the absolute value signs here, I could get rid of that minus sign. And I'm just going to integrate from D to D plus A. And this is logarithm. And the only thing that's going to depend on time here will be the current. And so I can rewrite it in the following way. And so this is the induced EMF. It's really the magnitude of it, sorry. Okay, that's the magnitude of the induced EMF in this black loop of wire. And if I wanted to find the current, well, it's just going to be delta V divided by R, whatever the resistance of the loop is. Questions on this one? Let's go back to the motional EMF problem. So this is a changing flux problem. I mean, changing magnetic, this is a case where the magnetic field is changing because the current is changing. Now let's go back to do the motional EMF problem. When I did the problem the other day, I said, we have a rod on conducting rails. I give it a push. And we said that if I don't apply a force to that rod to keep it moving at a constant velocity, it's going to eventually come to a stop. Let's derive the velocity of the rod as a function of time. So let me draw my rod on the rails. The distance between here is L. And I'm going to draw big X's. And it goes on that way. Okay, so we deduced the fact that in this particular case, if the V of the rod was this way, to the right, my current that's induced was counterclockwise, and that produced the magnetic field, that produced the magnetic force to the left that opposes the velocity of the rod. So we'll say that way's negative, to the right's positive. And we know that delta V, motional, is B, L, V rod. We know that the current that's induced is this divided by the resistance. But this thing, F sub B, the magnitude of it is just I in motional L times whatever that magnetic field is. These two vectors are 90 degrees from each other, so sine of 90 is 1, so I don't have to worry about the sine term. And this force, if I put the signs in, this force is to the right. And this is going to be equal to ma, the mass of the rod times the acceleration, which is m dv rod over dt. So this force is opposite to the direction of motion. All right, so our I here is this term. And then let me put this all the way through. Let me combine all the terms. I'm going to divide both sides by m. I don't want to rewrite this. I'm going to cheat. I'm going to just do this. And then I put everything with v on one side and everything with dt on the other. So I separated variables. Guess what I'm going to do next?
Integrate?
I'm going to integrate. And and I'm just going to integrate it this way. I'm going to say, okay, this integral is going to be plus a constant. And I can evaluate the constant at any time. I just usually evaluate the constant at the end. After I do this, I'm going to exponentiate everything. And so that's going to give me but what's e to the c?
It's a constant.
Yeah, and a lot of folks don't like if I write it as c again, so I'm going to do the following. Well, I'm just going to call it k. I have to figure out what k is. I mean, I could have done it here, I guess. Right? I mean, I could have done it because I need to know what the speed was when I gave it a push. Well, that's my initial velocity, isn't it? So I'm going to let v rod equals v initial at t equals 0. So that makes v rod equal v initial, whatever it is, e to the minus b squared L squared t over mr, where r is the resistance. And so if you wait an infinitely long amount of time, the velocity goes to zero. Of course, there's friction in there, so it's not, you don't have to wait an infinitely long amount of time. Okay?
Hey, Professor,
Yeah.
can I ask a quick question about the system? So for the f sub b pointing to the left, is there a way to prove that to yourself via the right-hand rule?
Yeah, yeah. I mean, yeah. That's what we did. I remember last week we went through. Went through that. So, okay, the
So
current.
you're curling your fingers towards the magnetic field that's already there, right? Not the magnetic field that's being produced because of the current?
Correct. So,
Okay.
let me put the direction of the current is upward, right? In that rod. It's this way, right?
Yeah. And then the magnetic field is into the board.
Okay, let's do
So if you
that.
point your fingers in the direction of the current and curl towards the magnetic field, then it should be to the left.
Yes. So it works.
Okay.
Okay.
I just wanted to double check.
So, but I mean, you asked a good question. What's another way for me to realize that the force has to be to the left, as opposed to the right?
Because then it would be speeding up.
Yes. So that's another way to look at it, right? If the force is to the right, this thing is going to speed up, and I'm not putting any energy into the system, right?
Yeah.
And it's like, that would be nice if we can do that, but it doesn't happen.
And then can I also ask about this last problem you just went through? You
Yeah,
went
yeah, yeah.
from in addition to a multiplication via the rule of exponents, right?
I'm sorry, say that again.
So the bottom line of the first column, where you have ln of the absolute value of the rod is equal to that stuff over there. On the right side, you went from an addition to a multiplication via the rule of exponents, right?
Yes, yeah, yeah.
Okay. Okay, thank you.
Yeah, I could have. Maybe it's easier if I evaluate the initial condition here, and then I exponentiate. I'm not sure. Somebody asked me about that. Why did you do it? Why did you evaluate the initial condition here or here? And I said I just chose that. It's up to you. All right, so now I'm going to do one. It's a little more complicated. It's a railgun. Both of these are actually textbook problems. So this is a railgun, essentially. So let me draw a picture of this. I want to find the velocity of my bar on the rails. And you need a special power supply to do this. You need a power supply that's going to maintain its current. It's called a regulated power supply. Otherwise, it ain't going to work. Okay. Not a battery, even though my picture shows a battery. You don't want a battery there. Okay. I made this short I mean, you can make this very long. Let me make these x's bigger. Okay, so the field's into the board. I close the switch, and when I close the switch, there's going to be a current this way. We'll call it I. And then that current is going to go through this rod this way. And according to the right-hand rule, the force on it is going to be to the right. Does that make sense?
Yeah.
But what happens as it goes to the right?
It'll speed up.
That's true. But the flux is changing, right? And it's going to induce a current in the opposite direction. So I total is going to be I minus I induced. Does that make sense?
Yeah.
And so the net force is going to be I minus I induced times L times B. We'll call this the power supply voltage. And so this is just going to be the power supply voltage over R. But this is going to be B L V rod over R. That's going to be the net force. Okay? And this is going to be equal to M dV rod over dt. And so now all I got to do is solve for V rod. So now I got to figure out a way to separate the variables. Oh, wait a minute. When is the net force equal to 0?
When the two currents are equal to each other?
Yeah, when the two currents are equal to each other. And so at the velocity in which these two equal each other, that's called the terminal velocity. So this thing is going to reach a terminal velocity. So you can figure it out from here, or I want to figure it out later, okay? So there's two ways. This is the easy way, okay? Somebody asks you to find a terminal velocity, you just show when this is true, right? I mean, just set these two equal to each other and you're done. Okay, very easy. But I'm going to do it the hard way because I want to derive v as a function of time. Okay. You don't want to find a terminal velocity the hard way. You want to find it the easy way. Okay. I want to try to rearrange things. I want to make this a little bit easier for myself. Let me multiply both sides by R and divide by LB. So let me write it like this. And then I'm going to put everything with a V on one side and everything with a dt on the other side. Make sure I did that right. Okay. and I'm running out of space. So I'm going to multiply through by -1. Just because I want to write it in this form. And now I integrate. When I integrate, what do I get? Does that look okay? I'm going to multiply. Is this okay with you guys?
Yeah.
Okay, I'm going to multiply both sides by b times L. But because I'm running out of space, I'm going to do this. And then I'm going to exponentiate. Where, again, k is e to the c. So I have to figure out what this is. At t equals 0.
Professor?
Yeah.
Is that on the one with the K in it, is that minus delta VS?
This one? Yeah.
Yeah, it's just cut off just barely. Just the subscript is cut off by the screen.
Okay, hold on a second. I will fix that. How's that?
Yeah, that works.
Okay. Although you probably can't see that side now. I'll go back and fix it.
No, that one's still visible. You're
Oh,
good.
it's still visible? Okay.
Yeah.
So at t equals 0, v rod equals 0. So that means then that this is 0 and this is 1. So that means that k is delta v sub s. So that means then and I'm going to solve it real quick. And so that's the velocity of the rod as a function of time. And as t goes to infinity, this term goes to 0, and the velocity of the rod ends up being delta v sub s over BL. So v terminal can be easily determined.
Hey, Professor.
Yeah.
does the negative sign on the delta Vs when you set it equal to K, does that not hold any significance?
When I determine the K,
Yeah, so when you just set T equal to 0, but then you found that K is equal to delta V sub S, is there a negative sign on the delta V sub S? Or does that not hold any significance?
oh, hold on a second. I might have made a mistake. Yeah, it is negative. You're right. Yeah, you're right. That is negative. So otherwise, this would have been a plus here. Thank you for pointing that out. It has to be negative V sub, delta V sub S. Yeah, that's important. That's just a mistake on my part.
No worries, thank you.
Okay. We okay with that? Okay. That was a hard, I mean, granted, that's a hard problem. If you look in the book, that's a red star problem in the book. It's not an easy problem because you have to set up this differential equation, but solving this equation is just like doing the capacitor problem for the RC circuit. So let's talk about a few more applications of Faraday's law. I mean, it's used in induction heating, tasers, electropneumatic valves, SID monitors. There's a ton of applications of Faraday's law. For example, the electric guitar pickup coil. You pluck the string on the guitar. That guitar string, which is is magnetic. It's near a magnet, so it becomes magnetized, and as it vibrates, you have a wire whose magnetic field is vibrating, is changing relative to the pickup coil. So the flux through that pickup coil is changing. There's an induced EMF and a current in that pickup coil that's connected to an amplifier where the signal is amplified and processed. Suppose we have a loop of wire rotating in a magnetic field. It's a simple loop of wire. Let's assume the magnetic field is uniform. That picture really doesn't indicate a uniform magnetic field, but let's pretend we have a uniform magnetic field because we're really trying to make the math simple. So let me draw a loop of wire of one turn for now. Okay. And we want to rotate it about an axis like that or like this. Let's say the magnetic field goes in or out of the board, and we rotate this loop of wire about this axis. So B is in or out of the board. And we're going to rotate it at the angular speed omega. The flux through this loop will be changing because the angle between the normal to the loop and the magnetic field changes. When the normal to the loop points down, there's no field lines going through it. When the angle is 90 degrees between the magnetic field and the normal to the loop, there's no field lines going through the loop. I want to know what the induced EMF is through this rotating loop of wire. Let me write down the flux through that loop of wire. For now, we're going to assume one turn, okay? The magnetic field is uniform, but the normal to the loop changes. So this is going to be the integral of b times cosine of theta. B is uniform, only the angle's changing. dA is just the area of the loop, or the integral of dA is the area of the loop. So but theta is changing. Theta is a function of time, is that. So phi sub b okay. So now what's the induced EMF? It's going to be d phi or minus d phi dt. What's the derivative of that with respect to time? Well, I'm going to get minus a sign, and that minus sign will cancel. And that's the change in EMF, the time rate of change of flux, or the EMF, in one loop. For n loops, we just multiply this by n. This is the equation for the AC generator. Okay, that's just the equation for the AC generator. So let me show you an AC generator. Okay, so I have here, it's hard to see still. Okay, sorry, I'm trying to get you to see both items, which is kind of tough. Let's see if I can do this. Okay, so this is, remember the motor I was showing you the other day? This motor can also run as a generator. So what I've done is I've hooked up power to the coils. And then I'm going to rotate the coil in the magnetic field. What do you notice? This is measuring the current. Notice that the current changes directions because I'm generating AC current. Of course, at the power plant, you rotate this faster, 60 times a second. Okay, so I'm generating AC current. Now I can also run this as a DC generator by using the split ring commutator as in the motor. And what you'll notice, just by changing that, the current will change, but it only changes in one direction. I think I got too big a magnetic field. Okay, it always stays in one direction because it's a DC motor, a DC generator. If I go the other direction, can you guys see the needle move?
Yeah.
Okay. And so that's a generator. Same thing with these guys. I have these little toys. So these are just generators. And hold on a second. And this one has a light bulb on it. So by me rotating a loop of wire in a magnetic field, I'm generating a current. Just to show you that these are motors operating in reverse, I have two of these connected to each other. Okay? I wired them together. Maybe it's hard to see. So I'm going to take one and try to spin it, and the other one will rotate. And the light goes on. Okay? And one of the things that happens is when they're disconnected, I have no problem turning this. But when I connect a load to it, it's very hard to turn it. Why is that? Why would it be very hard to turn it when I'm running a current through?
Is it because of the induced current?
Well, we got to be careful. It's not induced. No, it is induced. I'm sorry. There is an induced current. What does the induced current do?
Well, I know it runs opposite, at least in some cases, to the normal current.
But doesn't it? It produces a torque on that loop, right?
Makes sense.
So because torque is mu cross B, which is N, the magnitude is NA I B sine of theta. A is the area of the loop, I is the current in the loop, and N is the number of turns. And theta is the angle between these two guys. And so there's an induced. Once you hook it up to something, you're drawing a current, it produces something called a counter torque, and it's harder to turn it. In fact, it'll want to slow down. You actually have to apply a force to keep it going at a constant speed. And this thing is called a counter torque. Okay? So this develops a counter torque when it draws a current. If I have an open circuit, in other words, this generator, if it's just not connected to anything, it's easy to turn. Other than the fact that I got to deal with friction, it's easy to turn. But when I hook up the bulb to it, you'll notice a difference. So when we're in class, I pass these around, so let the students see the difference. And when you spin it, you notice when you connect the light bulb, it's harder to turn it. You actually have to increase the amount of torque you're applying to keep it going at a constant speed. So that torque produced by the induced current is called a counter torque. And that happens when you connect a load to a generator. Now, why is this important? Why is this thing important? I mean, this is hugely important. What comes out of your wall socket? This is how we generate electric power. Right? This is how we generate electric power at the power plant. This is hugely important. That's why Faraday's law has huge application. This is the biggest one probably, okay, or one of the biggest ones. That we can generate electrical power using this idea, rotating a coil of wire in a magnetic field. Okay, so in your house, omega is 2 pi times the frequency, which is 377 hertz. The frequency is 60 hertz. So in your house, this is going to be 170 sine of 377t. This is the amplitude, right? This whole thing is the amplitude. In your house, you get this. If you square this and take the average, you get 120 volts. We'll talk about that in chapter 33. So this is hugely important. So this is how electrical power is generated. At the power plant, and it's stepped up with transformers to high voltages so that I squared R is low, because when you step up the voltage, you reduce the current because of conservation of energy. When it gets to your house, the voltage is stepped down, and then you have the energy delivered to your house. So yeah, this is a hugely important application of Faraday's law. This is why this is one of the most interesting chapters in the course, because of the applications. Okay. And I've already demonstrated to the counter torque. After we come back, I'm going to do a problem with the motor where we calculate everything. Okay. Now the difference between the DC generator and the AC generator is that this is the AC generator. DC generator is the absolute value of this thing. Okay, that's the only difference. And so you use a split ring commutator for the DC, where the AC, they're separated. Okay, they're called slip rings for the AC generator. And of course, the AC generator also can operate as an AC motor. Okay, I don't want to keep going here. So when we come back from lunch, I'm going to do two more things. I'm going to do an example with the motor, with the generator, and then I'm going to do the last topic is something called back EMF, which I think a lot of you folks have experienced. Have you ever worked, for example, with a drill? Okay, so let's take a break. Come back in 20.